In today's lesson, we will start acid-base chemistry. As is often the case when learning a new topic, we need to start with some basic definitions to get you ready to discuss more complicated aspects and understand some of the motivations for the study of this topic that we'll go over in class. By the end of this lesson, you should be able to identify the pH ranges of acids and bases at 25 degrees Celsius, have a molecular understanding of how we define acids and bases, and identify the conjugate acids and bases if given a base or an acid. First, let's talk about something that you've heard of in daily life, pH. From previous experience, we may know that neutral is equal to pH 7, acidic is less than 7, while basic is greater than 7. Let's look at some particularly interesting aspects of this chart that has all of the pH ranges of common substances. First, where is the soda? Now think about what acid rain is known to do to statues. Imagine that happening in your mouth if you're sipping on soda all day long. It's more than just sugar. Diet soda is still going to wreak havoc on your teeth. Now notice where blood is and how small of a pH range that blood can be. Many of our bodily functions create acid or bases as products, so we'll need to figure out how blood can manage to keep such a small pH range with all the acids and bases being added in. Also, look at tap water. Notice it's not evenly centered around 7. Why is it more likely to be acidic? We'll answer all of these questions in the next chapter. Now let's get into the meat of how all of these acids and bases work so we can try to explain some of these things. Now on to looking at what is happening at a molecular scale. What makes something an acid or a base? There are several different definitions. For the most part, we'll work with the Bronsted-Lowry and Lewis definitions, which are both listed here. The Bronsted-Lowry definition of an acid says that acids are proton donors. The Lewis definition is in parentheses, that an acid is an electron pair acceptor. We'll now walk through one example of this with a chemical equation, and then show a quick animation of what is happening. So here, we have the lone pair of the oxygen coming and forming a bond with the hydrogen, which leaves us with H3O plus over here, and since it's taking the hydrogen away, it's leaving NO2 minus. This gives a pH of less than 7. Here, we have it in a little bit of an animation. In this case, we have formic acid donating its hydrogen atom to water. This leaves the formic acid with one less hydrogen, being formate. Notice that while we often write it as shown above, with the hydrogen simply being left on its own, in actuality, it is being given to the water molecule to make H3O plus, as shown in the little animation. So which is right? Well, technically, you should always write H3O plus. But on an exam, or in real life, when dealing with chemical equations, you are allowed to just write H plus. Bases, in opposition to acids, are proton acceptors, or according to the Lewis definition, a base is an electron pair donor. Here, we have the nitrogen's lone pair that's capable of forming a bond with the hydrogen, leaving us with the same structure that we had, but with now a bond to the hydrogen, giving us a plus ion. Since the water has a hydrogen taken away, but it keeps both of the electrons, it becomes a hydroxide ion. And we can show this in a little animation as well. Here I have ammonia and water, and the ammonia will take a hydrogen away from the water, leaving it as a hydroxide. In both of these animations, and as we write each of the equations, do notice that this is an equilibrium arrow, meaning that this is in a dynamic equilibrium and is consistently going forward and reverse. There are 3 definitions of bases in acids that we use. We've already seen 2 of these, but let's discuss how each of these are related and when it's useful to think about each concept. The simplest is called the Arrhenius definition. In this case, we think of acids as H plus donors and bases as OH minus donors. While this works well for substances like HCl and NaOH, what about something like the NH3 example that we saw earlier in the video? We need a definition that includes molecules like NH3. The Bronsted-Lowry definition instead says that acids donate an H+, while bases accept an H+. This encompasses all of the Arrhenius acids and bases, while also including those nitrogen-containing bases like NH3. The last definition we will discuss in more detail in later videos, but for now, know that we can also talk about acids and accepting lone pairs, and bases as donating lone pairs. Earlier in the video, I demonstrated this by showing an arrow going from the location of the electron pairs and taking the hydrogen away from water. The Lewis definition includes all of the Arrhenius and Bronsted-Lowry acids and bases, but extends it even further to include molecules like boron trifluoride, a silver ion, or carbon dioxide. And we'll look at these mechanisms later on in the chapter. Now let's talk about something called a conjugate acid or base. This is a term that is always relative to the acid or base that we started with. So for instance, if we have acetic acid and we remove the hydrogen, the resulting species is a base because the reaction is in a dynamic equilibrium. Since it's on the product side, we'll call it the conjugate base. Similarly, if we add a hydrogen to a base, the resulting species is an acid because of the dynamic equilibrium, and so we'll call it the conjugate acid. Let's do some examples. Pause and see if you can decide the conjugate base of the weak acid shown here. Since we have H2SO4, to find its conjugate base, we need to remove a hydrogen. This leaves us with HSO4- as the conjugate base. Please notice that I did not remove both hydrogens. I only removed one. Once again, try solving this one for yourself before continuing. If we want to find the conjugate base, we need to remove a hydrogen. This leaves us with Cn-, or the cyanide ion, as our conjugate base. This is the last example of acids, and we'll move on to bases. Pause and try this on your own, and then come back. Here I have given you a more complex example, except that it's actually very similar to the acetic acid example that we started with. The hydrogen from the COOH group will be removed to give us this structure. You'll want to remember from 1A the structure of this carboxylic acid group, and when you see it, remember that the hydrogen is removed to form the negative ion. Now let's talk a bit more about bases, focusing on these nitrogen-containing compounds. These will have a similar structure because of the nitrogen. It will have the nitrogen with 3 bonds. Each will then be able to form a 4th bond to a hydrogen, leaving us with a positive ion. Let's first look at the simplest example and just put 3 hydrogens on the nitrogen. The lone pair can act as an electron pair donor and form a bond to another hydrogen. Take a moment and pause the video if necessary and decide what the conjugate acid of this structure would be. We add a hydrogen to the base, leaving us with NH4+. We'll make the base structure a bit more complex now by adding a methyl group to 2 of the areas that were hydrogens. For the most part, we'll treat this identically to the ammonia example. In organic chemistry, you will learn how these different groups affect the properties of the base. Please note that you won't be responsible for naming these types of molecules. You'll learn more about the nomenclature in organic chemistry. However, I will often start using the proper nomenclature to start getting you used to hearing it. This will make the transition into organic a bit easier for you. For now, pause the video and see if you can figure out the conjugate acid for the dimethylamine. We will do the same thing that we did with the NH3. We'll add a hydrogen, which leaves us with this structure. Notice once again it's a plus charge because when the nitrogen bonds to the hydrogen, it does not take the electron with it. That stays with the OH- group. For our last example, let's do one where we have a double bond to the nitrogen. This doesn't actually change any of the rules. There is still a lone pair on the nitrogen that is available for bonding with a hydrogen. Pause the video and decide on the conjugate acid before continuing. We add a hydrogen just like before, leaving us with the structure shown here, and again with a positive charge on the nitrogen. Hopefully, after watching this video, you know what an acid and a base is, how to identify them, and how to identify the conjugate acid and bases of the species.